Hello everyone, welcome to our most recent webinar, Photochemistry Made Easy, Batch and Flow Chemistry in the PhotoCube. My name is Gellert. I will give you a short presentation, and after that I will hand over to Mathieu, who will perform a live demonstration using the PhotoCube. Here you can see the outline of this webinar. I will start with a brief introduction on continuous flow photochemistry and on some recent applications using the PhotoCube before the live demo. We will finish our webinar with a Q&A section. In our previous webinars, we covered the HQ Mini Plus and the HQ Pro, which are instruments for hydrogenation reactions. If you haven't seen these webinars, you can use the links below to rewatch them. Just a few words about ThalesNano for those who didn't follow us before. ThalesNano is a company specialized in developing and manufacturing benchtop reactors, mostly for flow chemistry. Our instruments are used mostly in pharmaceutical labs, but also in academic labs and industrial labs such as agrochemical, petrochemical, or labs at the flavors and fragrance industries. Most of our instruments are used for discovery, so they are fairly small-scale instruments. By now, we sold more than 1,400 instruments all over the world. Our instruments are mentioned in more than 700 publications, and we have more than 17 years experience in working with flow chemistry. We are very proud of the fact that two of our products, the H-Cube, which was our first product, and most recently the H-Genie developed by ThalesNano Energy, received the prestigious R&D Top 100 award. Let's just take a really brief look on our instrument portfolio. If you look at the top left, you can see the Ice Cube, which is an instrument for exothermic reactions. In the Ice Cube, you can cool down your reactions to -70 degrees and perform exothermic reactions such as nitrations or so. If you go to the right on the slide, you can see the Phoenix flow reactor and the flash vacuum pyrolysis platform. These instruments are for high temperature chemistry. For example, the Phoenix flow reactor can heat solutions up to 450 degrees, and the system can be pressurized even up to 200 bars. So you can perform high temperature, high pressure chemistries using the Phoenix flow reactor. If you look at the bottom left of the slide, you can see the gas module next to the H-Cube Pro. The H-Cube Pro is a benchtop continuous flow hydrogenation reactor. We have talked quite a lot about this, so we'll not go into details today. If you look to the right, then you can see the H-Genie and next to it the Phoenix flow reactor. So the H-Genie is a standalone hydrogen generator, which can be used for both batch and flow applications. If you connect the H-Genie to the Phoenix flow reactor, then you have the ability to scale up hydrogenation reactions even to a couple of kilograms per day productivity. And if you look at the very right bottom of the slide, then you can see the PhotoCube, which we will show you in details today. So just a couple of words about photochemistry in general. Photochemistry is well known for quite a long time, and if you look outside the window, you can see plants and which use sunlight for photosynthesis. You can also think about your body in connection to vitamin D, for example. Nevertheless, for some reason, if you go into an organic chemistry lab, you will find that not too many of them are engaged in photochemistry. Why is that? What is wrong with photochemistry? The first reason probably is that traditionally photochemistry was performed using high energy UV light. And UV irradiation can pose safety concerns. And also it is a bit difficult to tune our reactions selectively. The other issue is related to equipment. To perform photochemical reactions, you need special equipment. For example, you need transparent material where the light can penetrate. And if you think about the traditional high or medium pressure mercury lamps, they generate quite a lot of heat. So you have to drive away that heat somewhere and somehow. So there is significant process complexity, and people tend to think that scaling up photoreactions is difficult or impossible. Nevertheless, if you look into literature, you can find some scale-up examples. So how and why did photochemistry become popular again in the last decade? I believe that this is due to the seminal discoveries of the Macmillan, Stevenson, and the Yoon groups. And also due to the fact that there was quite a significant development and advancements in terms of technology. Just think about the development in flow chemistry and also in terms of lightning technology. Nowadays, LEDs are available. You can buy them. They are quite easily accessible. Okay, and if I want to do photochemistry, should I go batch or flow? Well, the superiority of flow photochemistry over batch has been reported quite a few times. But is flow photochemistry really superior over batch? If you look into the literature, Booker Milburn and his group carried out a detailed study in which they compared 3 reactors, one immersion well reactor and 2 photoreactors, and they tested 12 reactions in these settings. Their final conclusion was that under identical conditions, the yields of these reactions were essentially the same. Identical conditions means that, for example, the concentration, the amount of light, the reaction times, and all these parameters were kept the same for the experiments. And this is quite important to make precise comparisons between batch and flow. So if I want to do flow photochemistry, why would I do it? On this slide, you can see quite a long list. Some of these points are generally related to flow chemistry, such as increased safety or fast heat exchange. I only want to highlight the first point, which is the improved irradiation. So if you look at the Lambert-Baird law, you will see that most of the incident light is typically absorbed within 2-3 centimeters of the solution, or sometimes even less. So if you have a big batch flask, a round bottom flask, then in the middle of that flask, there will be basically no light. However, if you use a meso or microfluidic reactor with narrow width, for example, our reactors typically feature inner diameters of 1 millimeter, then the light will be able to penetrate through that narrow width, and you can achieve almost complete illumination homogeneity. So that was all what I wanted to say as a general introduction, and now we will focus on the PhotoCube. When we started to develop the PhotoCube, we wanted to make a photoreactor which has a broad application area. We wanted to be able to perform both batch and flow reactions in the same instrument. We wanted an instrument which is capable of performing reactions on the milligram scale, but also capable of producing compounds on tens of grams scale per day. And finally, we wanted to cover the UV visible light range as much as it is possible. So to achieve these goals, we decided to use LEDs as our light sources, because LEDs are non-thermal emitters, so they don't generate too much heat, so it is quite easy to cool them down. LEDs cover most of the visible light and part of the UV spectrum, and they are really affordable, small and versatile. Apart from LEDs, we also used 3D printing, not just for fast prototyping, but also for manufacturing, as you will see it later on. The key advantages of the PhotoCube, as I previously mentioned, are the fact that you can perform both batch and flow reactions in the same system. So for example, one typical application can be that you do a screening with 8 vials, let's say, in batch, and then you perform a scale-up reaction in flow. The PhotoCube features 8 inbuilt LEDs, and there is no need to change the light source between experiments, and multiple wavelengths available at the same time. In addition to that, you can control the temperature of your reactions. Mathieu will show you these in details. In the rest of my presentation, I will walk you through a couple of examples or potential applications which we have performed using the PhotoCube. This will be a benzylic bromination reaction, a copper-catalyzed atom transfer radical addition, and an iridium-nickel dual catalytic decarboxylated CC coupling, and a Minishi reaction which we adapted to flow conditions. So here is the copper-catalyzed atom transfer radical addition. This reaction was performed in batch, so this was done in a vial. This reaction is done using green light irradiation. You can see that the wavelength which we use is 523 nanometers. That corresponds to green light. And the reaction is catalyzed by a copper dep2 chloride complex. On the right side of the slide, you can see some reaction time conversion data. The PhotoCube features 4 LED panels. You can tune the intensity of the LEDs, and you can also switch off some of these panels. So if you look at the blue rectangle, blue squares, those show the results when the PhotoCube was used on the highest intensity. Basically, full conversion was achieved in an hour. If we lower the intensity to 30%, or we just used one panel for irradiating our mixture at maximum intensity, the reaction proceeded much slower, as it is illustrated by the gray circles and orange triangles. In these cases, the reaction took 2 hours to complete. If you compare these results with the literature, you will see that in the literature a reaction time of 20 hours is reported. So as a take-home message, I can say that reaction times quite often can be significantly reduced by using more light, so by providing more photons as reagents to your reaction mixture. The next example is the benzylic bromination. This will be the reaction which Mathieu will show you. This is a really quick reaction. It only takes 82 seconds. And the reaction can lead either to a mono or a dibrominated product. Because it is a quick reaction, we use this to illustrate the scalability using the PhotoCube. We performed a scale-up up to 55 millimole, which means approximately a 180 milliliter solution of the starting material. On the right side, you can see that this amount of material was processed within 14 minutes. and the conversion to the desired monobrominated product, compound number 2, stayed constant between 80 to 90% throughout this processing time. We also had some residual starting material and the dibrominated product in less than 10%. These results correspond really well with data reported in the literature. My next example is decarboxylated coupling using iridium-nickel dual catalytic system. In this coupling, compound number 3, the product, features a carbon-carbon bond, which is an sp2-sp3 bond, and this is quite interesting for pharmaceutical research. We performed this reaction under numerous conditions, and we compared it with literature data. The literature reference was performed on another commercially available flow reactor. As you can see, full conversion can be achieved both at 395 nanometer or 457 nanometers. 395 nanometer is violet light, so it's just on the edge of the UV, and 457 nanometer is blue light. Under our best conditions, which you can see in entry 5, we performed this reaction with blue light irradiation in 20-minute reaction time at 50 degrees Celsius, and we were able to achieve full conversion with a 69% isolated yield. This yield corresponds to a throughput of 1.3 grams per an hour for compound number 3, the product. So in a working day, you would be able to make 8 to 9 grams of this product without any hassle. How does the flow setup look like? We have 2 streams in which we introduce the starting materials. In one stream, we have the aryl halide, the DBU, the nickel catalyst in DMA. In the other stream, we have the carboxylic acid, the iridium photocatalyst in DMA. These feeds are merged together in a simple tea mixer, and then they are introduced into the PhotoCube. So for such setup, you need 2 pumps, a mixer, and the PhotoCube. And the final example is the Minishi reaction. First, I just want to show you a general equation of the Minishi reaction. In the Minishi reaction, typically you take a heteroarene and you generate alkyl radicals from a carboxylic acid, and your product will be an alkylated heteroarene. One of the ways to generate alkyl radicals from carboxylic acids is to form an intermediate from N-hydroxyphthalimide and the carboxylic acid, and then use that intermediate under photochemical conditions to access the alkyl radical. Why would you do this reaction in flow? The typical batch procedures are quite low yielding sometimes and always time consuming. Making one compound using these procedures typically takes 27 to 48 hours. So we wanted to cut down the reaction time, and that's why we started to adopt this reaction into flow. We divided the reaction into 2 steps. The first step is the formation of the NAP, or N-acyloxyphthalimide ester intermediate. So for this, we performed an optimization in the Phoenix flow reactor. Under our optimized conditions, in one feed, we had the DIC, which stands for diisopropyl carbodiamide, and in the other feed, we had all other reaction components. These feeds were merged together in a simple tea mixer and then were introduced into a loop installed in the Phoenix flow reactor. We were able to achieve 96% HPLC yield of the NAP intermediate in a 30-minute residence time at 80 degrees Celsius temperature. We didn't apply pressure for this reaction. Once we optimized the formation of the NAP ester intermediate, then we performed the telescoping, in which we merged together the feed coming out from the Phoenix flow reactor with the feed of the heteroarene mixture with the TFA iridium photocatalyst in DMSO. So the mixture of the NAP intermediate and the heteroarene was introduced into the PhotoCube to afford the product, which is numbered compound 1 here. Both reaction steps take 30 minutes, and as you can see on the right side of this slide, we had a throughput of 570 milligrams of compound number 1 based on isolated yield. Finally, we started to build a little scope on this reaction using a variety of carboxylic acids. As you can see, our yields are equal or a bit above literature data. We also performed a scale-up reaction up to 1 gram of starting material. That whole process was performed within 2 hours. So here you can again look at the specifications of the PhotoCube. I will thank you for your kind attention, and I will hand over now the word to Mathieu.
So thank you, Gellert. So this is a PhotoCube and what it looks like in its laboratory environment, in its setup, almost ready for reaction now. So it has 2 main parts, so the reactor unit and the control unit. So they can be separated from each other. So you can put the reactor unit apart. And so it's connected via communication and power cables. So it's convenient if you would like to control your reactor from outside the fume cupboard. It's a safety feature. So let's first talk about the reactor unit. So above, it has a cap that covers the photochemical reaction chamber. So it has some ventilation holes here and on the side. And on the side, behind those ventilation holes, you have 4 cooling fans that regulate the LEDs. So if your reaction requires a thermal regulation, then you need to connect an external water cooling system. Like in my setup, I connected to the tap water, and you can see the inlet, the water coming in here and coming out here. So the water inside, so it cools down the photochemical reaction chamber via a fan and a heat exchanger that is at the bottom of the reaction chamber. You can also use like other external cooling systems such as a chiller. So it's not only especially a tap water, and it may be even better a chiller, like if you want to control like more accurately the temperature of your reaction chamber. So now inside the reaction chamber, you have 4 panels. So on each of those panels, you have the LEDs for the 6 colors, for the UV, and for the white. And at the bottom of this reaction chamber, as I already told you, this is a heat exchanger. So now you know with this PhotoCube, you can do both batch and flow chemistry. So you have different kind of holders to do this kind of chemistry. So for example, to do batch chemistry, you can have this kind of holders. You can put up to 4 vials of 30 milliliters. And so you put it inside the reaction chamber like this and put the cap back on, of course. So you have a magnetic stirrer inside to make your solution homogeneous. So you have also different sizes, of course. Like, for example, I can show you here, like, it's a 4 milliliter vials. You can put up to 8, and the same way you put inside. It is important to say that you can also have some custom-made sizes. The only limitation is it has to fit inside the reaction chamber. And those holders are can be very easily made because they are 3D printed. So now, if like me, for this reaction, you'd like to do some flow chemistry, so you have another kind of holder, and this is these holders. So in this holder, so you have FEP, in my case, FEP tubing that is called around the holder. So you can customize the volume of it. Like, for example, in my case, it's a 2-layer, so it's about 8 milliliter loop. So now I'm going to put this loop inside my reaction chamber as I will start the washing, and I close it. And then I'm putting the outlet here in my flask. Okay, I'm going to start the washing now because it will take a couple of minutes before I can start the reaction. So I'm just turning on the pump. So meanwhile, I'm going to talk about the second part, the control unit. So it has an operating status LED, which can be green, like everything is all right, like now, or it can flash in red. That means like you are, for example, in a forbidden configuration. I will show you an example in a couple of minutes. And then you have your first rotating knob, which allows you to manage the speed of the steering, but in the case of the batch chemistry, of course. In my case, I don't need magnetic steering. So then you can decide if you want to enable 1, 2, or 4 panels. So most applications actually benefit from an homogeneous irrigation when the 4 panels are activated, and it will be the case in our live experiment. Then you have a switch to decide between a low mode and a high mode. So what's the difference? So in high mode, the LEDs can operate at a higher current with a higher photon flux. So, but if you are looking for a combination of different wavelengths, that means you have to work in low mode. So in other words, single wavelengths operation can be achieved in both high and low modes, while low mode you can achieve different combination of colors. So, and then you have a screen display here that shows you the temperature and also the last settings you set. So here, right now, you can see only the temperature since I didn't put any settings, but I will do in a couple of seconds. So now I'm going to talk about those gray rotating knobs with which you can select the wavelengths you want to apply. So I'm going to give you an example. So let's apply the red color. So you can see it increments from 10%. But then if you would like to add another wavelength, like for example, blue, and you can see it flashes in red. So as I just told you, a combination of colors, so more than one wavelength, can be achieved only in low mode. So I have to switch to low mode, and then my LEDs are green again. So it is a allowed configuration. More than only two colors, two wavelengths available, you can also like add some other with different intensities of lights, as you can see. And after, you can also see a little chart that shows you like all the wavelengths you have enabled with a different intensity. So, but now let's set the setting for our reaction. So I'm going to deactivate all but the violet because our reaction will be done under violet. So we are working in high mode with the 4 panel selected. And I have also to turn on the water. Okay, now before the injection of my starting material, let me show you the reaction we are going to do. So we are going to perform a benzylic bromination. So starting from this para-methyl acetophenone, we are going to add NBS, so N-bromosuccinimide, to have this brominated product. So it's going to be performed under violet light, as I showed you, with the 4 panels for most homogeneous reaction and in high mode. So it's going to be in a quite high flow rate of 6.12 milliliter per minute, as the reaction is quite fast, so only 82 seconds of residence time. So now I'm not going to wait for the steady state for the purpose of this demo. It's not here critical at all, but it is something that can be important in some cases. So I'm just going to start the injection of my product just by switching. And now, while it's injecting, I just want to have a few words about the steady state. So although the flow is continuous and then the concentration is supposed to be uniform, there's actually 2 times it is not. It is precisely at the interface you created when you change from your washing solution to your reactants, what I've just done now. And reverse, when I'm going to change from my reactant solution to my washing solution again. So indeed, you have some diffusion coming out from this interface that create a gradient of concentrations and so make the concentration of your material different. But after a while, the steady state is reached. So you can see it on a graph like this, hypothetical ideal concentration profile I drawn, and you can see in real life, it's different. Like it doesn't go to the steady state right away when you start the injection. So now I'm going to start the collection. So by switching just to my collection flask. Okay, just one last word about this steady state. It is important to notice that on small scale synthesis, like this one, the steady state may not be often met, but it is like a really important phenomenon to consider on larger scale. So what I'm going to do now, I'm going to stop the injection as we may have enough product to show you our reaction work. And so I'm just going to switch back to the washing solution. And Now I'd like to have a few words about this setup, this part of the setup, because those are two modules that are not part of the PhotoCube specifically. Like they can be also modules for the other instruments, like for this, for example, this pump is used with the HCube Pro, and this valve module, it is used with the Phoenix, for example. So how does it work? When I actually, there's my starting and washing solution here. And when I switch the valve on my on this module, it switches from the my starting material to my washing solution. So it makes it quite convenient. And then it goes through my HPLC pump head, and then my product goes to the loop, my reaction chamber, and then it goes to my reaction task. Okay, I think you can maybe see it on the video. You could see a change of color, and it is like a gradient, and it gradually disappears, like you can see. Now it is only my washing solution that is here, and here you can see it is a slightly yellowish because I still have some of my material coming out from here. But right now it's become like totally colorless. That means like all the solution, my washing solution have passed through the outlet. And so that's time to put it back to the waste because I have collected enough product now. And so that's the product. You can see it right now. Okay, so thank you for having watched this demonstration. Now it is time to answer your question with my colleague Gellert. Thank you.
Okay, I hope you enjoyed the demonstration. Let's look at the questions and what do we have here. So the first question is whether our users can acquire customized light sources in the PhotoCube. Currently, we only offer the PhotoCube with the configuration which you have seen now, but we are always open for custom requests. So if you are interested in such a request, please send us an email and we'll see what we can do. What would be the max volume we can use in the PhotoCube? That is our next question. I'm not sure what kind of volume you are talking about, so I will split my answer into two bits. The first one is for batch reactions. The reaction chamber is a 7 times 7 times 7 centimeter cube shape. So in principle, that limits the maximum volume. With our current standard holders, the biggest ones can fit vials with a 30 milliliter internal volume. If you go into flow, our loop sizes range between 2 and 20 milliliters. But obviously, because we are talking about a continuous flow procedure, you can push through the instrument much higher volumes as well. The next question is, what if you want to optimize to only 254 nanometer irradiation? Unfortunately, we don't have 254 nanometer LEDs. In the UV range, the best which we can offer is the 365 nanometer LED. Can we perform refluxing reactions? Unfortunately, no, not really. And how much is the maximum pressure the vials can hold? We don't supply just a couple of vials with the PhotoCube. These are standard vials. So So if you want to pressurize the vials, you need to buy special vials which can be pressurized. Otherwise, if you don't want to pressurize your system, you can just use simple vials, simple screw cap vials. Can we do pressurized reactions? So in batch, you cannot really do pressurized reactions except if you ensure that you would have the pressure vessels for that. In flow, you can hook up the tube or the loop to a back pressure regulator, and then you can pressurize your system. Can we scale up to a kilogram scale? No, the PhotoCube is not for kilogram scale. The biggest scales would be probably in the 100-gram area per day if we are talking about continuous production. How do you perform moisture and air sensitive reactions? I would say that you do it in the same way as you would do for any other batch or flow reactions. You put sealed vessels in terms of batch reactions, you put sealed vessels into your instrument. So you need to take care about inertization beforehand. For flow reactions, you would need to use pressurized vessels with only small pressure. For example, the typical procedure is to have a vessel with a septum on top. You put some nitrogen or argon pressure on that, and you inject your tube into that vessel through the septum and start to pump under slight pressure. What is the maximum RPM of stirring? The maximum value is 1400.
It's 1500.
Sorry, 1500. So 1500 is the maximum RPM value, but you won't be able to exploit that RPM in all cases. The RPM which you can apply will depend on the size of the stir bar and also on your solution. If you have a solution with a lot of solid particles, you might not be able to reach such high values. What are the parameters? Sorry, I'm just having trouble with a little bit of trouble with the next question. What are the parameters can be controlled during reactions? So in terms of batch reactions, you can control the stirring rate, you can control the wavelengths which you apply, and you can control the temperature, and obviously you can control the time you use for irradiation. In terms of flow reaction, it's basically the same apart from the fact that you don't use magnetic stirring there. Maybe I forgot to mention that you can also control the light intensity. So not just the wavelengths, but also the light intensity. What is the alternate for photoreactor the customer can use? For example, in place of the H-cube, they can use batch reactors. In terms of photochemistry, the classical or old school solution is using immersion well reactors, for example, with medium or high pressure mercury lamps. So that is one of the classical ways, I would say. What are the other two modes in the panel? So we have, can we show? Yes, we can. So we have this switch here. This can switch between 1, 2, or 4 panel irradiation. And we have this one here. We call it low and high. And this sets the current. So in high current or in high mode, you apply higher current, but you can apply high mode only if you do single color irradiation. If you go to low mode, you apply a smaller current, but you can work with multiple colors at the same time. Can you use the HQ Pro and the PhotoCube together, I assume? Yes, in principle you can use it. However, for the PhotoCube you need to use polymer tubing like FEP or PFA, and those will typically not be able to handle 100 bar pressure, so you would need to work at lower pressures. So the next question is whether we can introduce any external gases. Yes, with the right apparatus, so like the gas module or a mass flow controller, you can introduce gases into the flow system. And then, for example, you can perform oxidations using singlet oxygen gas. The next question is, in flow setup, how many LEDs are there per milliliter? Do you know what the can you please clarify this question, because I'm not, I don't understand the question. For cooling we use water, but is there any specific temperature of water? So for the demo, we used just a simple water tap, but you can hook the system up, and that's what you would normally do. You would hook the system up to a chiller or a thermostating unit, which most likely will work with a coolant solution, a specific coolant solution, and then you can control the temperature of that solution, and in exchange you can control the temperature in the reaction chamber. Can we handle slurry material? In principle, yes, you can handle slurries. You just need to make sure that your slurry and also the pump which you use will be compatible with the tube size, so there will be no clogging. Most likely you need a peristaltic pump for flow applications. If you work in batch, in principle, slurries are not a problem. What is the pressure of circulating water? I don't know a value for that. We usually provide a flow rate range in which you can ensure efficient thermal control, but let us get back to you with more details. Can we use multiple wavelengths simultaneously? For example, 395 nanometer and 457 nanometer at the same time? Yes, you can. Mathieu will demonstrate it. You switch to low mode, and then you can turn on multiple colors like 395 and 457, so blue and violet at the same time. The next question says that as you connect it to a micro HPLC pump, what is the minimum and maximum flow rate? So in the current setup, we use an HPLC pump. Yeah, that's correct. This can work between 0.1 and 10 milliliter per minute. But quite often, and for some of the applications which I showed you in the presentation, we use syringe pumps. And with syringe pumps, we often work in the microliter per minute range. But the choice of the pump will always depend on your specific application, depending on what kind of residence time and what kind of loop size you use. Is the magnetic stirrer comes as standard, or can we place the reactor on a third-party magnetic stirrer? The magnetic stirrer is a standard part of the PhotoCube, so you don't need any external stirrer to handle it. All right. I think we answered all of your questions. So before I thank you for your attention, I want to say a couple of words about our upcoming webinars. So the next webinar's date has not been announced yet, but we will do that next week. And you can see that through LinkedIn, or you will receive an email if you are on our mailing list. So please keep your eyes open. The next webinar's date will be announced next week. You can also review our previous webinars on the HCube Mini Plus and the HCube Pro. For that, please go to www.ThalesNano.com and follow the links there to find the webinars. And with this, I will thank you for your attention. I see that some questions still started to come up, but we will just answer those in emails later on. So thanks again for your attention, and see you during our next webinar. Bye-bye.